It is removing an electron. It's the energy required to remove an electron. So I actually wanted to go backwards, and I forgot that I wanted to add this part. Oh, Jiminy Christmas. I gotta go back so far. When we look at our, remember, it's being recorded and posted for posterity. I gotta sometimes be careful.
In 5 years, Corbin will go through all of your lectures.
Ooh. If we went through and looked at the orbital diagram and we started placing, say, electrons in. Okay, so let's go through. What element have I shown so far? Helium, because 2 electrons. Okay? So when we're talking about ionization energy, it's the energy required to remove one of those electrons. Right? So what we're talking about is, remember, we have the vacuum all the way up the top. How much energy does it take to grab that one electron and put it out there? Okay. Well, that gap is just that, right? It's just that, whatever that number is, that's what it is. Okay. What happens if I say go up to neon with 10 electrons? So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What happened to the gap? Gap gets smaller. That's ionization energy. That's all it is. Okay? So if we go through and kind of apply how these things stack out, we could go through based off of our orbital diagrams and predict the general trends that we would expect for ionization energy. Kind of make sense? Okay. So here we're going to jump a whole bunch of slides, and I resume recording. So noble gases are unreactive. Yes, as a general field. There are noble gases that will react. Okay? We need special conditions to typically get them to react. Helium, I don't think reacts with anything. I don't think there's been a case where it's formed compounds. Xenon, on the other hand, yes, does form compounds. Not easily, and it has to be forced to happen, but we can form them. Why such a big difference? Harder to break up? But then that would suggest that bigger nucleus xenon shouldn't be making compounds. Xenon is making compounds. What makes a compound?
Shared bond.
A bond. What makes a bond? Shared electrons between the atoms. Why might it be harder for helium instead of xenon?
Combination valence shell is full.
They all have full valence. Where are xenon's electrons with respect to helium's electrons?
Low energy versus high energy electrons?
Xenon's electrons are in a much higher energy shell, which means they're more reactive. Helium's are in a much lower energy shell, which means they're less reactive. So to get xenon to react, yes, I can do that because I'm using the electrons that are already the highest energy to put them into a bond, but it's already high energy. It's not a big deal.
But you have to force it.
But we pretty much have to force it, and it only works with certain elements, okay, to make that connection. Okay? So ionization energy is an entirely separate concept because in ionization energy, there's no other element. Okay? So I can understand where you were going with that. The noble gases, they don't react. So why are we looking at their ionization energy? Their ionization energy has nothing to do with their reactivity. Ionization says I have an atom with its electrons, and I remove an electron. What would be the most likely electron for me to discuss removing? The highest energy one, the one furthest on the outside. Okay? So when we talk about ionization energy, we're always talking about removing the highest energy electron. Okay? If we go through and look, we've got 2 rules. In general, your ionization energy increases as we go from the bottom to the top in a group. We just talked about that, sort of. Xenon to helium. Why is the ionization energy going to increase? Where is helium's outermost electron versus xenon's? Helium's is in the first orbit or energy level. Xenon's is in the, what number row? 5th, 6th, 5th. 5th energy level. That 5th energy level is so much closer to the vacuum, it's a smaller jump. So cool, that trend makes sense. Okay? But just like atomic radius, maybe we got things to worry about. What happens with ionization as we increase from left, or as we go from left to right? Okay? What happens there? It still increases. As you go from, I always get my left to right. Okay, so why might that be the case? Why is it going to be harder to remove that electron? Where's the electron getting placed? Left to right? The same energy level. Why is it going closer to the nucleus? Stronger positive charge. Okay? So cool. We have explanations that work out pretty well for both of those. Anybody in reading those trends have a snagging, nagging thing in the back of your head like this doesn't feel right, like something's wrong here? Nobody? You're all like, cool, those totally make sense, we're good. About those two rules. So we've got rule 1, rule 2. Is there anything about the language in those rules to make you go, there's something that's going to bother me?
Usually when you go from the top to bottom.
What's that? What does it mean when we say in general? Not always. Okay? So here we're like, oh, these are the rules to allow us to do this. Okay? Well, these aren't officially rules. There are exceptions to these rules. And this is something that I would like to point out is not an exception. Okay? What we have presented here are not rules, but trends. If we want to understand the rules, we actually have to look at the electron configurations. Okay? I think this is really neat, so we're going to spend some time talking about it. Okay? So let's go through and look at actual ionization energies. Okay? This plot can be a bit difficult to interpret. We're changing the atomic number on the x-axis, and we're plotting the ionization energy on the y. Okay? So if we go to the very first number on our atomic number, 1, what would we have? Hydrogen with 1 proton. So this dot right there is hydrogen. Everybody see that little red dot? Hydrogen. If I now add 1 more proton, what happens? I'd move to helium. That's what they're showing with this line. We're showing the line as we go across left to right. Okay? What happens as we go from hydrogen to helium? The ionization increased. Did that match the trend?
Yes.
Yeah. Okay? The nucleus, or the atom is getting smaller, which means the electron is going to be that much harder to remove. Okay? For those of you saying, well, how big of a difference? We don't really care. Notice there's no numbers on that, so don't stress. Okay? We're concerned about that trend. Does that make sense?
Mm-hmm. Yes.
Okay? What happens when we go down a column? So we go from hydrogen to lithium. Okay. They thankfully labeled lithium for us so we can see that. Okay? But that's 1 more proton. We're starting out the next row. What happens when we go from hydrogen to lithium? What happened to the ionization energy? It dropped. When we went down a column, should we expect the ionization energy to decrease? Yes. The electrons are getting further from the nucleus. They're in higher energies. And so if we look, we can see that trend. We see left to right increases, 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 increases. Okay? Down a column is a little bit harder to see, but in general, whoops, I'm in a different color. Decreases, decreases. Just pretend that I'm connecting those dots appropriately. Kind of makes sense? Thank you. Kind of, sort of? Yeah. Okay. So let's take a moment. Let's remove that. And let's start with saying, well, where does this stop working? Okay? Because if we look, it's not just straight lines up and straight lines connecting straight across, right? We do see there are these weird jagged things in there. Okay? We see a bunch of weird stuff happening in here, right through the middle, right? What's happening in those? These are our d orbitals. D orbitals just F everything up, so we stop looking at them. Don't look there. Okay? But even if we ignore the d orbitals, what's happening in here? We're still seeing some weirdness happening. Okay? So what is that weirdness? Okay? To get to that, remember I said what we're talking about is electron configurations. Okay, so let's take a look at one of those weirdnesses. Which weirdness do you want to look at? We'll simplify it. Nickel's in the D block. So, no, we just said we're ignoring that.
You said you wanted to look at one of the
Okay. So one of the weird things that's not in the D block. And I'm going to narrow your choices. We can either look at red or we can look at green, because there's two hiccups there, right? Oh, fun. Okay, we'll just put it to whoever can shout the loudest.
Green.
Green.
Green it is. We'll take a look at green. What elements are we picking, okay, for this? So what elements are we trying to figure out our electron configurations for? Well, remember, we started with lithium. Down here, we moved up to 1, which would be beryllium. Oh, dude, sorry. I was totally offset. You're right. Boron, carbon, nitrogen, oxygen. Okay, so we said we want to look at green, so let's go through and look at the green one. I want to look at the electron configuration for nitrogen. Okay, so one option, we can just jump with the cheats that I've been throwing out there, just jumping straight to the end. Nitrogen's in the second row. 2, it's in the P block. P, it's the third column of the P block. 2p3. Okay. Conveniently, that's all we really need to look at, but officially we're going to draw it all out. Okay, because we wanted that practice.
Okay.
Yeah?
Yeah.
Yes.
Oh, that was it.
Just a green? Okay. Oxygen. Okay. Fourth column, we're going to get 2p4, 1s2, 2s2, 2p4. Cool? Okay. That makes it obvious, right? We can totally tell.
No. Sure.
No. Okay. What happens when we ionize? We are removing an electron. Okay. So if I remove an electron from nitrogen, so here we go, remove electron, what would the symbol be for my nitrogen? I didn't ask for the electron configuration, I asked for the nitrogen. It should be an N and it should be a +1. I'd write that +1 in the upper right-hand corner because that's where I specify charge. Okay. Not proton necessarily. It's the balance of our protons and electrons. What would our electron configuration be?
The blank after the plus sign is for 1, 2, 2.
I see what you're saying up there. Yeah. Okay. What happens to the oxygen? It'd be O positive. So I said electron configurations give us the answer, right? Do we have the electron configurations?
Yeah.
Do we have the answer?
No.
Maybe, but we don't understand.
Maybe, okay, but we're missing something. We're missing a piece, okay? So let's poke a little bit closer at it, okay? If we went through to try and evaluate our difference on trying to deciding what's going on with these, let's take a look at our electron configurations for just the nitrogen, 1s2, 2s2, 2p3 versus 2p2. The difference happens in those p orbitals. So I really don't care about the s orbitals. Those are ultimately going to be irrelevant to this trend because
Different energy.
They haven't been removed, like there was no ionization.
they're the same. They haven't changed. So I don't need to evaluate. Okay? What I do need to evaluate is those p orbitals. Okay? Well, when I think about the p orbitals, is it just a singular orbital? No, it's actually multiple, right? So if I looked at nitrogen, it's actually 2p, 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 right? And if I were to place those 3 electrons in there, what would it look like?
One on each one.
One on each. How about once I ionize it, once I remove that electron? Do I still have all 3 2p orbitals?
Oh,
Do I still have all of those orbitals?
Yes.
Yes. 1, 2, 3. Now let's place the electrons. 1, 2. Does that give you the answer?
Yeah.
A little bit. Okay, so we got a brave volunteer. What's the answer?
I don't know the answer. I just know it's closer to.
It's closer to. Okay, what do you see?
So on oxygen, all three would still be filled. There would still be
Okay.
one in all of them.
Let's go through and look at the oxygen and see what its comparison would come out as. Okay, and I conveniently did not provide enough space, so there's our oxygen with our 3 2p orbitals. It started 1, 2, 3, 4, and it becomes 1, 2, 3. Yes?
Yeah, sure.
Okay, so now we've got both halves of our puzzle to evaluate. Does anybody see something? Got an inclination that maybe this is what's going on here? I saw it firsthand here, and then we'll go back there.
I'm thinking there's since there's less space to move around for the electrons, there's not as much energy for them to kind of jump around, whereas there's only 2 electrons, the nitrogen, so there's more movement, more energy that would cause a higher ionization.
No, because if I have more space, wouldn't these be happier to lose an electron? If they'd be happier to lose an electron, what would their ionization be for nitrogen? It should drop, right? Where'd it go? And instead, nitrogen's spikes.
Right, I'm saying it's increasing because aren't they moving?
We've given it more space to move. So your argument is our electrons have more space to move. Shouldn't they be happier? If that's the case, then the ionization energy should decrease because we're happy to have the electron removed. We aren't happy to have the electron removed because it's actually higher
Maybe I'm just
than our oxygen.
That's why oxygen's happier, because they're not fighting with, like the orbital, how you said, like, they're going the opposite ways.
So oxygen, we have a different potential to explain here. Here we have that kind of repulsive effect. Do we have that repulsive effect anymore? So no, oxygen could be like, hell yeah, get rid of that. Okay? So we could use that as a pretty solid argument to explain why oxygens would have dropped. Would it drop enough to explain that difference? Possibly. Okay? There's another argument that comes in. One that, as an argument we've already discussed. If we look at argon, what's its outermost electron placed? Outermost electron configuration for argon, so not up on the slides.
3.
Third energy level, yes, for argon, 3, P,
5, 6.
6. Okay, what comes after the 3p orbital? 4s. And some people, I'm not sure, isn't it 3d? Well, remember, our periodic table shows the fill. What happens after the 3p? 4s. We didn't jump to the 3d. The confusion there is you're like, well, we added an extra orbital. Shouldn't it move to the 3d? And it didn't do that. We had a big conversation on Tuesday, about our d orbitals being offset there. What was our argument for why that offset should exist? It was symmetry. And we said the more symmetric, the more prettier. I'm going to use word choice, and I'm going to switch that to beauty. Okay? Which of these two is more beautiful? Nitrogen starts as a beauty. When I try and remove an electron, what does nitrogen become? Ugly. Disney didn't like Beauty and Ugly. Pretty sure that didn't get recorded. Okay. So let's walk through that. Okay. Ionization energy. Okay. We have to remove an electron. This requires energy. So in the case of nitrogen, I come up to nitrogen, who's nice and happy, as a beauty, and I say, I have this stick, and I'm going to beat you with it. Okay. At the end of this beating, you will look like a beast. Are you going to put up a fight? Yeah. Okay. So what does that mean? Nitrogen's saying, hell no, don't do that. What happens to its ionization energy? It goes up. What happens to oxygen? Okay. We start unsymmetric as a beast, and we become a beauty. Okay? And for those of you being like, oh, oxygen's totally going to accept that. We are still removing an electron, hence the stick analogy. You now start as a beast. I come up to you and say, I've got this magic stick, and when I beat you with it, you will become a beauty. You're still going to be like, that's going to freaking hurt. But all right. Okay? And for those of you going, that is absolutely not true, no one in their right mind would do that. Have you ever heard of plastic surgery? Okay? That's not just a pleasant, we just make you look pretty. Okay? They literally pummel the crap out of whatever they're targeting, okay, to change it. Okay? We have a symmetry argument to explain that change. Oxygen still needs, I still need to add energy to remove that electron. Okay? But oxygen's going to put up less of a fight for that. Nitrogen, on the other hand, is no way in hell is that going to happen. So nitrogen's ionization energy spikes, oxygen's sinks. It's the combination of all of those effects that's creating the exception. It's not an exception. It's applying what we understand about electron configuration. It's only an exception if you don't understand what's happening. Which is kind of neat. Okay? So there's Beauty and the Beast. I think that's fun, personally. I really like that analogy and stumbled into it one day in class. It was fantastic.
Sorry for ruining
Okay. I don't think you ruined it because I'm pretty sure I didn't hear the last thing. But there was lots of head sinking and covering of mouths and oh my God in the back. So it's probably good it didn't get recorded.
Was it though? So we established there's a difference between getting to another energy level. Is there a difference in establishing the second orbital versus the third orientation? Like is the third one harder to establish than the second?
I'm not sure I'm following.
When you're feeling your energy levels. So, okay,
Going from the second energy to the third energy?
No, going from, say, like 2p, 2p, P3.
Okay, and jumping between those. There is an energy difference there. As soon as we've placed an electron in it, that orbital ever so slightly goes up in energy, which is why we go to the empty ones before we start pairing.
Right. I'm saying versus filling the first orbital and the third energy level. Is there a difference in energy to fill the second versus second to third?
I think I see what you're saying. The refinement between that is not worth evaluating in this class. Okay. We can talk about that more after class. I'm going to say that's not something we should really be discussing for a larger extent.
Seeing the opposite rotation is a concern, right? I was wondering if that played into it.
It could play into it in a very minute effect. Let's not dig that far.
Gotcha.
Sometimes we just want to go skin deep. Okay. Electron affinity, not in your textbook. Don't stress a whole lot about it. Electron affinity is doing the opposite of ionization energy, and that's the important thing I do want you to know about electron affinity. Okay. So in ionization energy, I'm required to put energy in to rip the electron out. Electron affinity, I'm taking an electron that's free floating on the outside. Electrons are unstable, and I'm now shoving it into the atom or into the molecule. That's going to release energy because we're going the opposite direction. Does that make sense? Okay. With that, I also want you to remember the next big kind of point with our electron affinity. What charge does the atom become? Yes, it is one of those two answers.
Negative.
Why does it become negative? We've added an electron to the atom. It has now a surplus of electrons. It becomes negative. Okay? So with ionization energy, our atom becomes positive. Electron affinity, our atom becomes negative, because we're looking at opposite directions of the electron movement. Make sense?
So if it's positive, it's negative, and if it's negative, it turns positive?
That, unfortunately, is an overstatement or an oversimplification of the process. When we're talking about both ionization energy and electron affinity, at least within the context of this class, we're not talking about a positive atom or a negative atom. We're talking about a neutral atom to which we either remove an electron or to which we add an electron. So if we start neutral and we ionize it, by definition, that is now saying it has become positive. Okay? If I start with a neutral atom and I now electron affinity it, what happens to the atom? It becomes negative. Okay? So in both of these cases at this level, we're only saying starting neutral. Could you remove more than one electron? Yes. That would call second ionization, third ionization, fourth, and there's tables of those. We don't care. First ionization, first electron affinity. Okay? Only do one. Does that work? Okay. So when we put all of those two pieces together, that's where we get electronegativity. Electronegativity we use as kind of one of the fundamental pieces for how we build Lewis structures. Okay? These are the rules that I would recommend you follow for Lewis structure. If you follow any other rule, where you're going to end up running into problems is right here with resonance. Okay? Other rules fall apart there, and what ends up happening is people sort of understandably make up different rules to allow for an answer to be explained. The extra rules they're adding in make no physical sense whatsoever. So that if you had to move into a class that required you to understand Lewis structure, you can't do resonance. 70% of organic chemistry is resonance. So when you talk to a general chemistry instructor and you just see like, oh, you know, what other chemistries are there? Like, which was your least favorite? When they say they don't like organic chemistry, it's probably because they didn't understand resonance. And it's probably because they didn't understand resonance because they didn't follow Lewis structure rules. They followed some made-up hand-wavy thing of just jamming stuff together. Okay? A somatic system as opposed to a logic system. Okay? Yeah, that was pretty decent. Okay? Kind of, sort of? Okay. These rules can be a little bit trickier to follow, which is why I understand why faculty try and push other rules, because they don't want to have to spend the time to explain them. These rules are so flippin' important to what I do as a chemist in organic chemistry, right, that I want you to have this particular set of rules so that if I see you again in OChem, I don't have to break you of all of your bad habits. I still have to break some of them, but I don't want to break all of them. Make sense? Okay. Once you have Lewis structure, then you can do shape. Okay? So we talked through CF4 on Tuesday, and since it is now Thursday and you had 48 hours, everybody has since gone back and watched that lovely video, right? Okay. You should probably go back and watch that because your test on Tuesday is going to test on this.
It's an hour long too.
And it's an hour long. Okay. Yeah, the average time I think watching it is closer to 2 hours, just to give you a heads up. Okay, because you take notes. Yeah. We talked about my heavy sarcasm with the pause button, but okay. So CF4, what I'm going to do is just jump straight to the structure. And this is one of the things that has to be kind of a challenge for you as students. If you ask someone to help you with Lewis structure, they almost undoubtedly can draw out all of the structure very, very quickly. And the way that they draw it does not involve any of these steps. Why? They internalized all of those steps, and you don't get to see any of that work. Okay? But because we showed all that work, I'm just going to draw straight out and get to that structure so that we can have that conversation, because you guys will never draw out this molecule in this fashion. Okay? There's our CF4. Okay? We just had that quick slide up on shaping. Okay? What is the shape then of this molecule? Okay? Coming up with that interpretation can be challenging. Okay? Because what we see here is a two-dimensional object. A two-dimensional object forced around a square. Why do we force it around a square? We'll see that here in a second. The shape that we're seeing here is not the shape of the molecule. Why not? Because it's three-dimensional. If we were to draw like a person, you might say, well, that represents a person. Is that a very good representation of a person?
Yeah.
No. Why not?
I don't know what he's thinking or what he is. What's his name?
We don't need to know his motivations. Okay? Very two-dimensional. We don't have that. Actually, I can see that secondary interpretation. It'd make it a little bit more, three-dimensional. Okay? So we lose a lot of information there. Why would we draw a person like that? It's easier for us to go through and draw. Even if we had a really good artist to draw that person out and show all of that kind of three-dimensionality, how long does it take? A lot longer. Okay? Does this get what we need to get? If it does, we stop there. If it doesn't, we have to keep layering in details. Make sense? Okay, so let's go back and look at our initial Lewis structure and try and figure out the shape. Okay? We've got the square around our center atom. This is how you do it. You look at each face of that center atom. So each face of the square. Are there electrons there?
Yes.
Are there electrons there?
Yes.
Electrons there?
Yes.
How many faces had electrons?
4.
Okay, so 4 groups of electrons. Okay? I haven't specified whether those are bonding or non-bonding or anything. I just said, are there electrons? That's it. Right? Because of that, I can now say that the electron geometry, there's just electrons there, the electron geometry is tetrahedral. Why does it go to the tetrahedral shape? Well, what do the electrons do when they see each other? They repel away from each other. So if we look at this system, there's only 4 groups of electrons. Those 4 groups of electrons need to get as far away from each other as possible. Okay? Does that make sense? Are they all as far away from each other as possible right now? Yeah? How far away are these 2 green groups? Okay. We could look at a variety of different ways of representing that. I would argue an angle here makes the most sense. What is that angle? 90. Okay, well, how about these 2? 90. See, you're totally right. They are all as far away from each other as humanly possible. There is nothing that isn't 90 degrees away from each other. For those of you that just said 180, those 2 are not 90 degrees away from each other, which means this drawing does not accurately reflect the shape. It is not a flat shape. It must take on the shape of a tetrahedron. Okay? That's those groups pushing away from each other. Why is the tetrahedron a pain to deal with? It is not an easy shape to draw in 2 dimensions. Okay? We can come up with writing systems to mimic where those groups are relative to each other for the tetrahedron. We could say those 2 bonds are in the same plane by showing them as solid lines. The angle between them for a tetrahedron needs to be 109.5 degrees. How many people read about 109.5? Cool. Don't worry about the bond angle. It's there. That's what it is. Don't stress. The other ones must also be 109 degrees. If I tried to draw one right here, what shape do I now have? I have a triangle, which means the bond angle is no longer 109.5. It becomes 120. Okay? Have a hard time with geometry or trig? Don't worry about it. Don't stress. Okay? You don't need to know the buildup behind those numbers. Okay? So what I'm going to do is say instead that that green bond is not in the plane of the paper. In fact, I'm going to say it's coming at me. So it's coming out of the plane of the paper towards us. How could I draw that? Okay. What happens is something gets closer to you. It gets bigger. So I'm going to show it getting bigger. Okay. The fourth bond is going into the plane behind our projector. You ever been drawing out on the road? Don't do that. Driving out on the road, okay, through the desert, right? You look out in the distance, and what does the road start to kind of do? Gets kind of wavy, gets smaller. We kind of see it's like there's sand blowing across the road. No, it's just an optical illusion, right? We get this kind of weird, kind of dashed looking thing. We've come up with a writing system to show or imply that information. That can be challenging for students to work with and deal with. That's one of the reasons why OChem is so difficult. Okay? Because you have to work with things in 3 dimensions. Okay? Kind of, sort of? Cool. That's our tetrahedral shape. Okay? Our electron group. Back on the previous slide, it didn't just stop with the electron group, right? We added a whole bunch of extra columns to it. And because you've all been studying it, you know what those extra columns are because you've now memorized it. Okay, so maybe we haven't done that. Okay, but there's a couple extra columns, and those couple extra columns are asking you to evaluate the groups of electrons. Okay? Are those groups bonding groups, or are they non-bonding groups? Okay? Why would that change the structure? Okay? What is a bond? Shared electrons. How many electrons in a bond? 2. Okay? If I have these 2 electrons and I'm not bonding them, where are they? They're right there. You mean like right next to me, right? Okay? I'm going to be nice now and I'm going to share with Boyd. You don't get both, dude. We're sharing. What happened to where the electrons are? They're a little bit separated. Where have they come away from my core or my nucleus? They've gotten further away. That means the gap between the electrons changes for bonding versus non-bonding groups of electrons. Because it changes, what is that going to do to your shape? Change it. Right? So what we'll end up doing is adding an extra layer or an extra term in here. That extra term is, instead of being electron geometry, we'll refer to molecular geometry. Which means a whole new, potentially new sequence of names to represent those shapes. Okay? So let's go back and look at this one. Okay? What is this group of electrons on the left? Bonding or non-bonding? Bonding. How do you know that's bonding? It's a line. How about the bottom one? So our 4 groups of electrons are all bonding groups of electrons. How many non-bonding groups do I have? To the center atom. None. I don't care about the outer groups. I'm only referencing the center atom. Right? That's why we put the box around it. That's how important that center atom is. So what does my shape become? Does it change from the electron geometry? No. There's no reason to change it because there's no difference between the groups of electrons, which means my molecular geometry is going to be tetrahedral also. Okay? Sometimes we'll refer to the molecular geometry as shape, okay? The shape of the molecule. Okay? In that shape, we're concerned less about the non-bonding pairs. We're concerned more about the bonding pairs of electrons. Kind of, sort of? Okay, so let's backtrack real quickly. We went through, we had 4 electron groups. That gets us to our tetrahedral electron pair geometry. We had 4 bonding groups, 0 non-bonding. There's our molecular geometry tetrahedral. Okay, that's how we read it. We at least got one, okay, so that's useful. How are we feeling with the rest of it? Should we do a thumb check?
Thumbs up good, thumbs down terrible, thumbs sideways sort of.
Not too bad. Okay. So does that mean we should do more practice?
Yes.
Yeah, that's probably a good idea. Okay? We got a bunch of different things up there. Which ones do you want to look at? CH4, I'm going to say no. SO3, I'll accept. SO3, I believe, was in the video? Yeah?
Yeah.
Do you want me to copy that one? No? Okay, sorry, SO3 disappeared. Okay. NH3. We'll do NH3 and then we'll do one of the other ones. So let's pick NH3. We start with our first rule, total to valence electrons. So how many valence electrons does nitrogen have? Okay, so that pause is problematic. We need to work on that, okay, because you're going to be tested on it. You'll see it probably is draw the Lewis structure, in which case you need to be able to answer that question and all of these. You will probably also see it as how many valence electrons does this atom have. We talked about 2 approaches to determining the valence electrons. Electron configurations, which is long and tedious and painful, or look at the Roman numeral above at the top of the column where your element is found. Nitrogen, I see you, give me a sec. Nitrogen, Roman numeral is 5, which means its valence is 5. Sarah.
Are you going to make us draw Lewis structures for our test?
Yes. Hydrogen. So for those of you at home, yes, you will draw Lewis structures for the test. Okay. Next one's hydrogen. How many valence electrons does hydrogen have? 1. Okay. Seeing a lot of people goof this. What does that 3 mean? There's 3 hydrogens. Each of those hydrogens brings in 1 valence electron. So I could write out hydrogen 1 3 times, or I could go through and say times 3, right? How many valence go into this? 8. Okay. And here's where we're going to kind of approach a subject on where it would vary further on down. Okay. We would go through, we need to pick a center atom. The center atom needs to be the least electronegative. Between nitrogen and hydrogen, which one's the least electronegative? Hydrogen. Hydrogen's the least electronegative. And you'd be like, well, dude, nitrogen's supposed to be a center atom. You're right. This is an abbreviation of the rules. We have to remember the full rules. The full rules also add the central atom needs to be the least electronegative that can bridge. We have to have at least 4, the ability to have at least 4 electrons around it. Hydrogen being in group 1 cannot do that. It can only max out at 2. Okay? So hydrogen can't bridge, which means hydrogen cannot be the center atom. Since I'm only given 2 elements, that must mean it's the nitrogen. I can now place the hydrogens around that nitrogen. You'll notice that when I go through and place them, I do place them off of the faces of a square around that. And that square I tend to organize in that fashion. Okay? The reason being, Lewis built his entire model off of cubes. Literally off of cubes. Okay? What is a flat cube? A square. If we go to that perspective, that can help us lay out where each of those atoms are located. Okay? Do you have a question, Kobe?
Oh, no.
Okay, just checking. Now the big difference. I want to add electrons. Okay, most rules just say add electrons. Okay? that extra little phrase there of adding electrons to the most electronegative is, to me, the most critical aspect of this. Okay? I want to make sure the atom with the most electrons, or most electronegativity, gets the electrons first. Okay? The analogy that I use for those people that have asked me about this is going to a potluck. Okay? If we all went to a potluck, what would we do? We would all, each of us, bring some food to the potluck. When we got to that potluck and we all had that food laid out as a nice big smorgasbord, are you only allowed to eat the food you brought? No, that would be pretty stupid as a potluck. Okay? The exact same thing is happening with Lewis structure and building a molecule. The molecule is a potluck. Each of the atoms brings electrons to the potluck. Okay? We can now eat anybody's food. Okay? So the argument of placing electrons around any particular atom at first is kind of problematic. So now let's add a next layer to this potluck analogy. At this potluck, who's going to eat the most food? Are we all required to eat the exact same amount of food? Because I have a feeling that that would make a lot of you very miserable. Because I can eat a lot more food than you probably. Okay? That's going to suck for you, right? Okay? So we eat food to our capacities. Okay? Here's where it becomes unfair. Who gets to eat first? Okay? It's all kind of random. We come up with some arbitrary rule system to come up with it. When we're looking at Lewis structure and models, it's electronegativity. Okay? Which is, if we look at an argument, it's the one that's biggest in the party and will beat the crap out of you if you take food first. Okay? Which could just be, your mom. Your mom's like, no, you can't eat first. Okay? And she hits you with her shoe. Like, okay? Somebody gets to establish that line, right? When it comes to molecules, it's electronegativity. The most electronegative is the one that has the most power. They dictate. Okay? Not only do they dictate, they say, I get to eat first. Which one was the most electronegative? Nitrogen. Okay? In our potluck, each of us gets to go through and collect food. Okay? We won't eat yet. We'll just collect it. We'll be nice, what is it, Miss Manners, right? We'll collect our food, but we won't start eating until everybody has food. Okay? So we all collect our food. Nitrogen's going to collect all the food it can possibly eat. Why? Because it's the most electronegative. Electronegative means it's attracting electrons to it. Well, how much electrons can nitrogen possibly eat? 8. It can achieve an octet. Okay? Why an octet? We could go through and say, well, there's 4 sides on this. Okay, well, why didn't I draw a triangle then? That has 3 sides. It would only be 6. Okay? Why is the 4 so big a deal? 8 electrons is probably going to be an easier connection. Lewis started his model looking at the simplest elements, not the most complicated. Okay, hydrogen and helium, too simple. So he's going to start with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. I just listed out 8 elements. What he recognized was a pattern is that there were 8 possibilities for electrons in that row. If I know that I need 2 electrons to make a bond, that means 4 bonds. What shape has 4 things? Squares, there's the square. That's why the octet is coming about. We're effectively making a noble gas. So now I'm going to start placing electrons. Okay? Doesn't really matter with the nitrogen, but I'm going to place them in pairs on each of the faces of the nitrogen until I've achieved my 8 electrons. Okay? This is where people tend to flip out at older rules. Well, nitrogen only has 5 valence. I don't have nitrogen. Nitrogen does not exist anymore. What do I have? I have NH3. Okay? So I don't care that nitrogen has 5 valence. That's irrelevant to the argument. Okay? By saying nitrogen gets 5 valence, that means you can only eat your popcorn that you brought to the potluck. Life sucks for you, unless you really like popcorn. Okay? We need to share all of that out. Right? Nitrogen has now consumed all of the electrons it can possibly take. So now hydrogen can go through the party. Okay? Well, is there any food left? Nope. We've already accounted for all of the 8 possible electrons. We're done. Hydrogen can't go back through the line. So hydrogen's going to have to deal with the electrons that are here. Nitrogen is nice enough to be like, hey, since you're chilling out on this side of me, sit next to me, I'll share some of my food with you. I represent that sharing by turning that into a line. Sitting in front of me, knows you don't have any food, here's a line. Sitting to the other side of me, there's a line. Okay? Satisfy octets. I need to make sure every atom has 8 electrons around it. When I go through and look at nitrogen, the line represents 2 electrons. So 2, 4, 6, 8. It has an octet. How many electrons around the hydrogen? 2. Is that an octet? No. You might hear words calling hydrogen as a duet. Hydrogen's an exception to the octet rule. The octet rule comes from looking at our second row elements, which have how many elements in that row? 8. Is hydrogen in the second row? No. Which means it's not going to 8. How many column or elements are in the first row where hydrogen is located? 2. How many electrons fit around hydrogen? 2. So the octet, if you will, for hydrogen is now satisfied. The octet for nitrogen is satisfied. Since all atoms have their octet satisfied, I do not have to worry about resonance. Okay? This structure did not have a formal charge. How do I know it didn't have a formal charge? Upper right-hand corner, it has to be indicated. Since it's not indicated, there's no formal charge. I don't need to worry about that either. Which means, what have I drawn? That's the Lewis structure. Cool?
Yes, sir.
What's the next step? 3D. Sort of with 3D. I know where you're going with it. We would go with our shapes. Electron geometry. How many groups of electrons are around that nitrogen? Okay, we look to each face and decide, are those electrons? 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 4 groups of electrons. What shape? Tetrahedral. Okay. We now go through and evaluate, well, are those groups of electrons all the same as each other? No, they're not. So that means the shape has a potential to change. Right? So I go through and evaluate. How many groups are bonding? 3, conveniently colored differently. I wonder who thought of that. And a non-bonding pair. 1. So what would the shape be for a center atom that has 3 bonds and 1 non-bond? Okay. Our shape is definitely trigonal. But now the question is that a 3-dimensional trigonal? Or is it a 2-dimensional trigonal? Okay. A lot of that has to do with the origin back to our electron geometry. Tetrahedral was a 3-dimensional shape, which means our trigonal here needs to be 3-dimensional. What is our 3-dimensional shape? Okay. A pyramid, pyramidal, I don't really care. Simple as that. Kind of, sort of? Okay. Do another one? Cool. Clear all those. NH4 plus. We'll switch it up and make it a little bit more challenging. NH3 CL plus. Oh my God, a different. Just relax. Okay. Nitrogen has how many valence? 5. Hydrogen has how many valence? 1. How many hydrogens are there? There's 3. We switched it up. Sorry for you, those of you still doing NH4. Chlorine has
6.
Learning our Roman numerals can be helpful for this. Okay. Can be difficult. 7. Who's looked at the practice exam? Who looked at the periodic table given to you on the practice exam? It's not Roman numerals, is it? I think I actually give you a number. I think it's 1, 2, 3, 4, 5, 6, 7. Yeah. So you don't even have to interpret Roman numerals. It's not a Latin, Greek, one of those classes, right? Last thing to deal with. This is how many electrons each of those individual atoms brought in. If we did that, what would the overall charge be? It would be neutral, because a nitrogen with its 5 valence would have the protons to balance it out. Okay? So each of those is now coming in neutral, which would mean the overall charge on that structure would be neutral. It's not neutral, and I know that because it's written in the upper right-hand corner. Okay? You'll notice when it's a +1 or a -1, I almost always circle it. It's a carryover from OChem. You're not required to circle them. It's just to help set it off. Okay? Make sure it doesn't get confused with a calculation. Okay? So I need to account for the charge. Well, if it's positive, I had to have added something, right? Okay, remember, the only thing I can add or subtract are electrons. To become positively charged, what did I have to do?
You have to lose an electron.
I had to lose an electron. I have to subtract 1 from the total. Okay? Trusting you on that. Is that right?
Yeah.
Okay, there we go. 14. I didn't actually look at the numbers. Okay? Yes?
I'm just kind of confused with how you know that it's neutral.
So when we went through to select those electrons that went into this structure, did we assume the nitrogen had any charge associated with it?
No.
Which meant our assumption was actually that the nitrogen had no charge. Okay? The only way you would change those numbers for your valence for those atoms is if you assumed it had a charge. Don't assume that. Always assume neutral. Okay? Unless otherwise specified. Here it's specified. Okay? Picking the center atom on this one is tricky because we have nitrogen, hydrogen, and chlorine. Hydrogen's the least electronegative, but can't bridge. Between hydrogen or nitrogen and chlorine, nitrogen is actually more electronegative than the chlorine. What you'll find from experience, and this is why this one gets a little bit shaky, is that the halogens can only form 1 bond. Can you bridge if you can only form 1 connection? No. Okay, which means our center atom is nitrogen. Okay? Because it's Lewis, I'll draw my square, and I will now place my atoms around it. This one's a little bit more interesting because I have 2 different types of elements to place. Where should I place the chlorine? On the top. Because you're placing it on the top, right? Okay. You place it on the top. Let's see what happens. What do we do now? We start adding our electrons in, not our valence electrons. If you want to say total valence, I'll accept that one. But even that, I'd be careful on, because as soon as you bring in the word valence, what are you going to start to do? Nitrogen gets 5. No, it doesn't. How many electrons does nitrogen get? 8 octets. Okay. Then there's a statement of if there's enough. Where should I start placing electrons first? Which one was the most electronegative? This one's a little bit tricky. It doesn't quite match up with our trends. Nitrogen's the 3rd most electronegative, followed by chlorine. Okay? So nitrogen is actually more electronegative than chlorine. Ultimately, it's not going to matter here, so we don't need to stress about it. I'm now going to place my 8 electrons around the nitrogen. How many electrons have I placed? 8. Okay. So nitrogen is now satiated and it can go sit down. I still have 14 electrons total. I've gotten rid of 8, which means I have 6 left. Where do I place those 6? Chlorine. Okay, so let's use a different color. There's a habit of people to start placing them between atoms. There are already electrons there. So don't do that. Okay? Place electrons first where there are not electrons. I've now placed 6 electrons around the chlorine.
So would you place them there if there were 2 more?
The reason why we would scale up to putting more electrons in there comes not at this stage. That comes ultimately at rule 6, satisfying octets by moving pairs. That's the only time you do it. Okay? We can now go through wherever I have a pair of electrons between atoms, I can draw a line, which means I end up with line, 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 line. Yes?
Yes.
Okay. Do all my atoms have octets? Yes. Since everybody has an octet, I don't have to deal with resonance. Formal charge is crossed out because you don't have to calculate formal charge per atom. That's 151. Okay? But what you do need to do is specify that that has happened, that the charge is somewhere dealing with that molecule. We specify that, or rather you specify that, by putting brackets around the structure, and then we would say that that structure is now a +1. Where do I write that +1? In the exact same place I write it everywhere else, in the upper right-hand corner, +1. Okay? In the video I talk about this because I'm inherently lazy and I consistently forget the brackets and the charge. So much so that I have misgraded multiple exams because I don't recognize the need to put that in until somebody does it correctly. And then I have to go back and regrade all the exams, and it sucks. Okay? So what you will sometimes see from me is not showing it at all or dropping in a little 7+. That's not a 7+. That's a very lazy bracket. Okay? So shapes, center atom. Tetrahedral, electron geometry, there's 4 groups of electrons. All of those are bonds. No non-bonds. We'll get tetrahedral for both the electron geometry and the molecular geometry. Yeah? How you feeling? Okay. Confident. Okay. Confidence. BF3. See what you can come up with. So, this one tends to trip up a lot of people. Boron, how many valence? Let's try that again. The Roman numeral above the boron is a 3, so there's 3. Fluorine, 7. There's 3 fluorines, so times 3 equals 21, and we get 24. Okay? Right away, we've got a mistake in the next transition. A lot of people are doing this. So if you're one of the people, I'm not trying to make fun of you. It's a common mistake. You transpose the meaning of where those numbers are associated. The 3 goes to the fluorine. What's the number with the boron? There's a 1 implied there. If it was a 0, there wouldn't be a boron, so we wouldn't write B. If it was any other number, we'd write it. So there's an implied 1 there. That means 1 boron, 3 fluorines. Be careful with it. It is super, super common. So boron, I can draw my box, fluorine, fluorine, fluorine. Okay? Next big mistake. People go, okay, I'm going to start putting electrons in. 1, 2, and right away I'm screaming at you. Like, I just put in 2 electrons. Yeah, you put both of them in wrong. Where do those electrons belong? Okay. So we can even go, okay, well, I'm going to do it here then, because it's now shared. Okay, I'll accept that. And then you go this, and now I'm screaming at you again. You're like, dude, stop screaming at me. We'll fix your mistakes. Why is that wrong? What's that? Where do I place the electrons? On the most electronegative. The most electronegative is fluorine, not boron. Now I'm not yelling at you. Then you go through. Ooh, I'm still agreeing with you. It's pretty good. Pretty good. And now I'm flipping out again. Okay? You were only allowed to put in 24 electrons. How many electrons have we drawn in? 26. You've exceeded the amount of allowable electrons. You have somebody eating invisible food. That doesn't work. Okay? That pair of electrons disappears. Don't start freaking out about it yet. We aren't to that rule. We've added till our total electrons, convert pairs of electrons into a line to represent the bond. Bond, bond, bond. Satisfy octet by moving electrons. Okay? Just because somebody did this, they removed that pair of electrons on the fluorine to the far right and said, there we go, boron now has 8 electrons. Fantastic, you are absolutely correct. Your structure still sucks. What happened to that fluorine? It now has only 6 electrons. Your structure still sucks. Okay? We're going to move pairs of electrons. That's absolutely valid. But we have to move them in such a way where we don't start ruining another atom's octet. Where can I place those electrons so that both the fluorine and the boron have access to them? I will place them between the atoms. I have a pair of electrons between atoms, which means I have a bond. Now I have a double bond. Double bonds don't just come out because, I just need to do it. That's complete and awful nonsense and crap. It frustrates the hell out of me if you couldn't tell. Okay? The reason double bonds come about is to satisfy these octets. That's why they're there. Okay? That's challenging. Okay, which is going to bring in the next phenomenal question. You're still losing points. I just went all through and did all that, and you're still going to take points away from me? Yes, because you're only a third correct. Okay. Did you have to move the pair of electrons from that fluorine on the right? No, you could have pulled them from the bottom one or from the one to the left. This is what resonance is talking about, which means, and I'm not going to draw all the electrons, but I would also have to specify these structures. All 3 of those would need to get included. Okay? And for those who are going, oh my God, that's so rough. That's why people tend to freak out at resonance and just try and ignore it. It is probably one of the most fundamentally important concepts to chemistry, and yet people just gloss over it. You can't gloss over it. Okay? Next big deal. I don't know why you're drawing that, but maybe we can talk after class.
I can see that's a big mistake.
You would have to draw all 3 of these. Crap. I lost the next big deal.
We have to draw the dots.
On a test, if you're out of time, don't draw the dots. If you've got time, yes, draw the dots. Okay.
I put this here because I thought people would make this mistake when they were looking at what you said.
Maybe what's coming from that is someone saying, okay, we see these 3 structures, and we're like, oh, well, what I'm going to draw is the blend of all of those, okay, which is what Greg drew up on the left. Very softly drawn right there, right? Electrons all the way, electrons, electrons, yeah?
20 electrons.
Okay. We would now have too many electrons in our structure. You could be like, well, I'm just going to delete a pair of electrons from each of those fluorines. Okay. How many electrons do you have around the boron? You've exceeded its octet. So that structure is invalid. Okay. What you could potentially be leading towards, which is not a favorite of mine, and I can't remember if our textbook actually shows it or not, is drawing something along these lines. And you're like, what the hell is that? Okay. If you drew a picture of me, right? You could draw one, right? Would you draw a different picture? Does that make me a different person? No. Okay? If you took a picture now, right? What would it look like? Thanks, Boyd. It would look like an angel, right? With flying wings. My arms are like kind of blurred. That's what this drawing is trying to depict. It's trying to show that the electrons have the ability to move all over the place. That's really neat. That is potentially a more accurate thing But if someone looked at that picture of me, they'd be like, dude, why does he have wings? Or why is he freaking weirdo? Okay? The interpretation, the ability of that isn't worth the effort. Okay? So it's a bad idea to draw that as well, in my opinion. There are some people that like it. I think it's a horrible idea. Okay? I'm sorry, I talked way too long. I apologize. We're done. No, stop. We're not done. Sorry. This is fast. I promise. This, last page. Okay? This is what I would recommend you purge onto the exam. When you get the periodic table, you purge this information. Okay? You get the arrows, your increasings, electronegativity, ionization, atomic radius. You circle those big red thing there and you identify those as the valence. You no longer have to hold that information until you see the question. Once you see the question, you go back to where you wrote it down and you're like, oh, there's the answer. All I have to do is answer that. That's such a stupid question, Mike. No, it's not, because people don't do simple test-taking strategy. Okay? Simple test-taking strategy can cover you for a lot of bases. Okay? Exam is Tuesday. If you have questions, feel free to send me an email.